Alright guys, so this is section 6.5, calculating the Gibbs energy of mixing for ideal gases. So what's the change in Gibbs energy when we mix some ideal gases? So we showed back in a couple sections ago this equation here. Gibbs free energy at some temperature and pressure is the standard Gibbs energy plus RT, nRT, ln of the pressure over 1 bar. Remember, this is 1 bar. And we also showed that the Gibbs energy is the sum of the chemical potential for each species times the number of moles of that species. Which means that for one species, one component, the chemical potential is Gibbs energy over the number of moles. So if we divide this equation here through by n, looks like this n cancels, but this gives us, these are just the chemical potentials. So this tells us the chemical potential of species I at some temperature and pressure is equal to the chemical potential of that species under standard conditions plus RT, natural log of the pressure over 1 bar. So let's look at this container right here, this picture. This is four containers, different volumes, 4 different gases, whole things at the same temperature and pressure. These barriers are removable, and so we're going to eventually remove these and allow the gases to react, but not yet. Now when we do that, we'll get mixing. That's what we're talking about. To find delta G of mixing, we have to know the Gibbs energy before and the Gibbs energy after, and delta G of mixing will just be after minus before. So we could write it like this. There's a lot of letters, but it's all pretty simple. So the Gibbs energy before, it's just the sum of the Gibbs energy of each of the components. So I had neon, krypton, argon, and xenon in there, which we can write as each of the Gibbs energies as the moles of each species times its chemical potential, which we have here. But we also know, we just reminded ourselves of that in the previous slide, that the chemical potential we can write as like this. So the Gibbs energy before will just be the moles of each of the species, neon, krypton, argon, xenon, for example, times this factor inside of the parentheses for each of those components. And afterwards, so remember we started out at everything being at the same pressure, but once we remove those barriers, now we're going to get everything expanding to fill the entire volume, and the partial pressure of each of those gases will be different than it was in its initial volume. So after the Gibbs energy is going to be, the same expression. The difference here is that the pressure of each of these gases is not going to be the same. Now it's going to be the partial, whatever its partial pressure is under the new conditions, still over 1 bar. And that's what all of these terms here are for. And so now, when we do the delta G of mixing, which is after this minus before, see the chemical potentials under standard conditions, these guys all cancel, they all go away, and what we get is this natural log term, RT natural log term, minus this one. And when we do the subtraction, natural log of A minus natural log of B is natural log of A over B. The 1 bars cancel, and we get the partial pressure of that gas divided by the total pressure before. So we get that expression for each of the components of the mixture. So this is delta G of mixing. This is just written up here again. But remember from Gen Chem, the partial pressure of a gas in a mixture is just equal to the mole fraction of that gas times the pressure, total pressure. Or if we rearrange this a little bit, the ratio of the pressures is equal to the mole fraction. And that's what we have up here. We have the ratio of the partial pressure to the total pressure. Likewise, the number of moles of a component in a mixture is equal to its mole fraction. That's this symbol here, the chi, that stands for mole fraction. I guess it might help to see it and to remind you about this if we write it a little bit differently. The mole fraction of component A in a mixture is just equal to the moles of that component divided by the total moles. So what we do is we come up here and replace each of these terms with the mole fraction, and this right here, the mole fraction, the moles of each of the components, we're going to write as the mole fraction times the total moles. And so we get this. So this term here, this, plus this term here is just like that. So that's what we did. We replaced the moles of helium, that's not helium, that's neon, with the total moles times the mole fraction of neon. Likewise, we replace the ratio of the partial pressure to the total pressure by the mole fraction. And we get this equation right here. And we can simplify this, and now we have a useful equation. Delta G of mixing is equal to nRT times the sum of the mole fraction of each component times the natural log of the mole fraction. Simple, pretty simple little equation. But just looking at the form of that equation gives us some good info, right? So we know, okay, so remember the mole fractions of any mixture always have to add up to 1. So the mole fraction of any individual component is always less than 1. That means that this natural log term right here, which is the natural log of a number less than 1, is negative. And mole fractions are positive numbers less than 1, and our t is all positive. So because of this term right here, we can see that delta G of mixing is negative. That tells us that mixing is a spontaneous process. Remember, that's one of our criteria for spontaneity, delta G being less than 0. Now let's simplify it even farther. Let's look at a binary mixture, just two components, call them A and B. We know that the mole fraction of one is equal to 1 minus the mole fraction of the other. So the mole fraction of B is equal to 1 minus the mole fraction of A. Plugging into this equation right up here and expanding it out, we see that delta G of mixing is nRT times the mole fraction of A, natural log of the mole fraction of A, plus 1 minus the mole fraction of A, natural log of 1 minus the mole fraction of A. Now, we showed back in section 6.2 that partial G, partial T, constant P is equal to negative S, the entropy. We can use that here. If we take the partial of, do delta G here and delta S here. So delta S of mixing is going to be partial delta G of mixing with respect to T, constant P, right here. If we take the partial of this expression right here with respect to T, the only T is right here, so it's basically just negative, the negative sign here, and everything else, just NR, sum of the mole fractions, natural log of the mole fractions. So we have two useful equations here. We can calculate delta G of mixing and delta S of mixing right here. So we'll look at this graph in just a minute. So this is what it looks like for a two-component mixture if you graph the delta G of mixing versus the mole fraction of one of the components. So let's look at delta G of mixing versus the mole fraction of one of the components for our binary system. When the mole fraction of either A or B is 1, so if the mole fraction of A is 1, that means the mole fraction of B is 0. We don't have any mixing, and delta G is 0 right here. Also, if the mole fraction of A is 0, that means the mole fraction of B is 1. There's just one component, no mixing, delta G is 0. It's a minimum, it ends up when we have equal mole fractions. Mole fraction of A equals B is 0.5. Let's look at the delta S of mixing. Looks like this. It's a maximum where we have equal components, equal amounts of each component. And it's 0 when we have either pure A or pure B. Pure A would be here, pure B would be there. And that makes sense because there's no change in entropy of mixing when there's no mixing. So only one component, no mixing. So now, okay, we can prove that for this two-component system where the maxima is. Remember that when you have a maxima or a minimum, the derivative of that function is 0. We for the entropy, we only have a maximum. We don't have a minimum. So, well, I guess the 2 zeros, but that doesn't really count. And so all we have to do to prove where the maxima is for that for this one is take the derivative of this with respect to the mole fraction of A and set it equal to 0. So to do that, just to remind you guys real quick that the derivative of the natural log of A with respect to A is 1 over A. So we're going to use that. So we're going to take the derivative of this thing right here, delta S of mixing, with respect to the mole fraction of A. Notice I wrote this in terms of just mole fraction of A, which we can do. So when we do that, first term here, so the NR is just out front. Chain rule again. Derivative of the mole fraction of A with respect to mole fraction of A is 1 times the derivative of natural log of this with respect to that is 1 over that. So we get basically, mole fraction of A over mole fraction of A, which is just 1. Derivative of this, we just get the natural log of mole fraction of A. So that's where these two terms come from. This one right here, the derivative of the natural log of 1 minus mole fraction of A is negative 1 over the mole fraction of A times the mole fraction, 1 minus mole fraction of A gives us a negative 1. And then the derivative of this with respect to mole fraction of A is negative. And then we get the natural log term. So it looks like this. Notice the ones cancel. And we're going to set this equal to 0 to find the maximum. So we know NR can't be 0. So that means that this stuff inside of the brackets has to be equal to 0. So what we have left is natural log of mole fraction of A minus natural log of 1 minus mole fraction of A, which we can just write as the natural log of the mole fraction of A over 1 minus natural mole fraction of A. Setting that equal to 0, we know that natural log of 1 is equal to 0, so this here has to equal 1. And we solve that for the mole fraction of A, we see that the mole fraction of A is 0.5. So the maximum entropy of mixing is when we have equal molar amounts of the two species. So a little example, let's calculate the delta G in mixing and delta S in mixing for a subsystem of that example we showed, that picture we had before. So just to keep it simple, two components, just let's say argon and xenon. We the pressure on the total pressure here is 1 bar. The temperature is 298.15. We have 3.79 moles of argon, 1.43 moles of xenon. So delta G of mixing, there's our little equation. Plugging in, and okay, so this 5.22, that just came from adding 3.79 and 1.43. R, T, this right here, this is the mole fraction of xenon. So that's just 1.43 over 5.22, natural log of that. This is the mole fraction of argon, 3.79 over 5.22, natural log of that. Plug in, you guys please check my work. I got, anyway, negative 7.597 times 10 to the third joules for delta G of mixing. For delta S of the mixing, similar, no T in front basically. Negative N, same N, R, same mole fractions. I got 25.48 joules per Kelvin. Okay, positive. Of course, that makes sense. Delta S of mixing is going to be positive, right? And finally, let's look at the driving force in this mixing. Remember, delta G is delta H minus T delta S, right? So if we solve for delta H, okay, we already calculated delta G of mixing. X is kind of out there. And delta S of mixing. So if we plug those numbers that we got in, negative 7.597 times 10 to the third joules here, plus temperature is 298.15. Delta S of mixing, 25.48. And basically 0. I get like 1 times 10 to the minus 10th, which is just rounding error. So it's 0. What that tells us is there's no enthalpy change associated with the mixing. And that makes sense because we know that in ideal gas, the particles do not interact. So there's not going to be any thermal energy transferred. So the driving force in this case is strictly entropy, which is, by the way, a really strong driving force.